All right, let's talk about one of the biggest headaches in software development. Code that feels solid one day and then becomes a fragile, buggy mess the next. So, how do we build software that's actually meant to last? Well, let's dive in and figure that out.
You've totally been there, right? You get a request that sounds simple. Hey, can you just add this one little feature? And then next thing you know, completely unrelated parts of your app are mysteriously broken. It can feel like you're walking through a minefield. So why does that happen?
Look, the answer isn't to work harder or write more tests. It's about working smarter. And we can do that by using a powerful set of guidelines called the Solid Principles. Think of them as a toolkit for creating flexible, easy-to-understand code that doesn't shatter the moment you touch it.
Now, what exactly are these solid principles? Well, SOLID is an acronym for 5 key concepts: single responsibility, open-closed, Liskov substitution, interface segregation, and dependency inversion. We could talk about these all day, but today we're going to zero in on 2 of the most impactful ones, the O and the L. Okay, first up, the open-closed principle. This one is a real game changer. It's all about designing your code so you can add new features without being terrified of what might break. It's about building a system you can safely add to.
The official definition sounds a little academic, I know. It says software entities should be open for extension, but closed for modification. But the idea behind it is just brilliant. Open for extension means you can add new capabilities, and closed for modification means you should be able to do that without changing a single line of existing battle-tested code.
Let's just boil that down to its core. The goal is simple. Add new stuff without messing with old stuff that already works. I mean, think about it. Every time you go back and change an existing class, you open the door to new bugs. The open-close principle helps us keep that door shut.
So that's the million-dollar question, isn't it? How on earth do you add functionality without actually modifying the original code? Well, the secret sauce here is something called an interface. You can think of it like a contract or a blueprint for what a class needs to do, without locking you into one specific way of doing it. Let me show you what I mean with a quick example.
Okay, so here's the scenario. You've got a class that saves invoices to a file. It's been working perfectly for months. Now, your boss comes along and says, we also need to save these to a database. The risky, tempting approach is to just crack open that working class and start adding new code. The solid approach, though, is to extend its behavior without ever touching it.
And this is what that risky way looks like. See, we've just opened up our invoice persistence class and shoved in a new save-to-database method. And yeah, it'll probably work. But we've just tampered with a class that was stable and reliable. We've increased the risk of breaking the original file-saving logic by accident.
Now here is the beautiful, solid way. Instead of changing our original class, we transform invoice persistence into an interface. That's the blueprint I was talking about. All it says is, hey, any class that wants to be an invoice persistence type must have a save method. Then we create 2 new, totally separate classes, database persistence and file persistence. Each one follows that blueprint, but implements the save method in its own unique way. Our original logic is now safe and sound, completely untouched.
This diagram really shows off the power of this new structure. We have our central invoice persistence contract, then we have database persistence and file persistence both honoring that contract. So what happens next week when your boss says, now we need to save to MongoDB? No sweat. We just add a new class. We don't touch the old ones. It's flexible, it's safe, it's fantastic.
Okay, let's shift gears to our second principle, the Liskov substitution principle, or LSP for short. Now, this one is all about making sure that when we create parent-child relationships between our classes, inheritance, that it all actually makes logical sense and doesn't create bizarre, unexpected problems down the line.
The formal definition here says that subclasses should be substitutable for their base classes without messing things up. In other words, if you have a piece of code that expects a parent class, you should be able to hand it any of that parent's child classes and it should still work perfectly. No surprises.
So here's the absolute heart of the matter. A child class must honor the contract, the promises made by its parent. If the parent class promises it can perform a certain action, then every single one of its children must also be able to perform that same action, no exceptions. This brings up a really interesting problem. What happens when our real-world logic clashes with our neat little class structure? What if a child class, for very logical reasons, just can't fulfill all the promises made by its parent? To see what I mean, let's look at the classic example with birds.
At first glance, this looks totally fine. A swan is a bird, and a penguin is a bird. Makes sense. So we create a base bird class that has a fly method. The swan can fly, awesome. But the penguin, it's definitely a bird, but it absolutely cannot fly. Suddenly, our seemingly logical design has a major contradiction.
So our bird class made a promise. It promised a fly method. When we get around to writing the penguin class, what are we supposed to do with that method? We can't actually make it fly. The only real option is to make it throw an error, which is basically our little penguin object shouting, "Stop! I can't do the thing you're asking me to do!"
And here's where it all falls apart. Imagine you have a function that takes a list of bird objects and tells every single one of them to fly. It works great for the swan, but the moment it gets to the penguin, our program throws that error and comes to a screeching halt. The penguin was not a valid substitute for a bird because it broke the fundamental promise of being able to fly.
The solution to this is just so elegant. Instead of trying to force all birds into a flying box, we create a more honest system. We have a base bird class for things all birds do, like eat. Then we create a separate flying bird interface for only those birds that can also fly. The swan uses this interface, but the penguin doesn't. Now our classes are telling the truth about what they can and can't do.
So let's pull all of this together. We've talked about being open to adding new things, but closed to changing old things. And we've talked about making sure our classes keep their promises. What's the big picture here?
Ultimately, following solid principles is the difference between building with a house of cards versus building with Legos. You know, with a house of cards, you touch one card in the wrong way and the entire structure comes crashing down. But with Legos, every piece is its own sturdy, independent unit. You can add new pieces, you can swap them out, and you can build incredible things without ever worrying that the whole thing will collapse. That's the kind of resilient software we want to be building.
So that's really the question to leave you with. Take a look at your own projects. Is your code a fragile house of cards, or is it a robust set of Legos ready for whatever the future throws at it? Because applying these principles is how you start building for that future. Thanks so much for joining me.